every day there's this.
All right. So when we're talking about, we talked about polarity yesterday. We kind of got to this point where we were going to be talking. Did we talk about this guy? I think we did. Did we talk about these?
Yeah.
Did I skip them?
No, you did. We did that.
Could you like at the end go over it?
So,
because like I didn't really fully understand.
okay. I'm recording it. What?
We did the next one.
Okay, I didn't think we did this one. Okay. Austin, there's the pass. Ksenia, take the owl next time.
Why?
Because I need that pass for other things, like Austin taking carts places.
Oh.
All right.
Yep.
So there is a difference between polar bonds and polar molecules. You can have one and not have the other, and vice versa. Okay, so let's look at an example of that. You have your chart there on the front of your packet. I don't have it in front of me. So what is the, this is hydrogen, what's silicon for its electronegativity? 2.5, okay? So when I subtract these, that's 0.4. That means that that's a non-polar bond.
No, it's 1.8. Wow. I only looked at sulfur.
Oh, my bad. Oh, yeah, you're right. Sorry, Libby. My bad.
They were trying to be
2.1, 1.8. All right. Either way, it's still a non-polar bond, correct? Okay. When I draw it out, it ends up being a non-polar molecule as well because there's equal distribution of those negative charges around that silicon. Over here, I have my hydrogen. What is sulfur? Somebody who actually wants to look at the chart this time?
2.5.
2.5. Again, this is a non-polar bond between the hydrogen and the sulfur. But notice that when I draw this, I have lone pairs of electrons. Anytime you have lone pairs of electrons, it's automatically going to be a polar bond. Because you have a concentration of those electrons very close to the central atom, those lone pairs of electrons are on that, it's going to give it a bent structure. So when you have a bent structure, that's also an indication that you're going to have a polar molecule. Even though these bonds are nonpolar, the molecule itself is polar. This end of the molecule is going to have a negative charge. This end will have a positive charge.
For the arrow, would that arrow just go straight out?
If you were doing an arrow for these, okay, it would be pointing from, this direction. And this end would be positive, and then you'd have another arrow pointing this way, like that.
So if you don't have lone pairs on the central atom, does that just automatically mean it's not polar?
Not necessarily. So for example, if we have this guy, there's not going to be anything on that central atom. And I think I did this one yesterday in class.
You did.
Okay. There's no lone pairs of electrons here, okay? But there's still going to be a concentration of negative charges here. So if we were drawing this, in this molecule, if we're drawing that, it would look something like that. Okay? Say that again?
Can you do like the S's instead?
S's, oh yeah, the symbol for charge, yeah. So this side would be negative, and this side would be positive.
So you're just like essentially like isolating them, so it's.
Yeah, I mean, think of it like, this end is kind of electron heavy, and this side isn't. As opposed to anytime you have lone pairs of electrons on the central atom, though, that's on automatic this. Okay. It doesn't mean that when you don't, it's automatically nonpolar. It's just this is like, you know, drop the mic, walk away. This is, you've got to kind of look at it and see. Fair enough? Did that help with polarity? Yes, sir.
That circumstance, like the same thing with like carbon, but it was two elements that were very, very close.
Electronegativity?
Would it still be not polar?
It would be probably non-polar, but it's still going to have a little bit of a polar tendency, like a slight polar characteristic. That's the word.
So like a range.
Technically, anything that's not completely balanced, like this guy, technically it's all polar. Okay, but you start to get that sliding scale, and when it kind of tips, then you're like, but they're only going to give you something that's pretty darn obvious. Okay, so.
Like if you had oxygen. Like, or not oxygen, but like something like, you know what I mean?
Yeah, something close. Yeah, I mean, technically, yeah, it would still have a little bit of a charge here and here, but it's not going to be a huge difference. So, all right, hybridization. So, when we talk about hybridization, what hybridization means that we're taking two things and we're kind of mashing them together. So you have hybrid cars, for example. They're combustion engines and they're electric engines or electric cars. So it's a hybrid, it's both. You have hybrid flowers where you have like a white flower and a red flower and you hybridize it and get a pink flower. Okay. So that's the idea behind what a hybrid is. We can have that happen with orbitals, and that happens with the sp orbital. So s orbitals are circles, p orbitals are like a peanut shape, and we can hybridize those and come out with, if we have one p orbital hybridized, then we would end up with these two sp orbitals. This is called an sp orbital then. This is a p, this is an s. Okay. So then we talk about hybridization. When we talk about hybridization, do I have a spot here that I can write? Let me insert an extra slide here so I can talk. Okay. If we have something like carbon, for example, okay, carbon has 1s, 2s, 2p, right? So this is carbon. That's carbon's orbital diagram, correct? Okay. What that tells us is that we have a different amount of energy for these two orbitals than we would have for this orbital, because this is slightly closer to the nucleus. What we know in reality is that all four of these electrons have the same energy. So what's happened here is this orbital and these orbitals have gone together and they've made sp orbitals because they have the same energy associated with them. They've hybridized. So where we had this before, we now have this coming out. Yeah, well, I guess there. That's this one right here. Okay, let me make this nitrogen. Now, better? These four things made these four things.
Oh, why is it only 4?
Well, there is a 1s over here too. We're just ignoring that because we're just looking at the outer stuff. This s can't, it doesn't have anything to hybridize with because there's nothing, there's no p orbitals there.
So the entire 2s orbital, both of the arrows, just become, they hybridize with the 2p and it becomes 1?
Yep.
Now, what if the 2p has down arrows as well? Would you add more orbitals to the 2p?
Yeah, there's still going to be, if this was oxygen instead, or let's make it fluorine, okay, it would still look the same way. Except you just have, that would be fluorine. Okay? All right. So let's say that, oops, we're looking at this and we're going to hybridize, we're going to bring together a couple different things. Okay? Let's make water, for example. Okay? No, let's not make water. Let's go back and make that carbon tetrachloride. Let's do that. CCl4. Okay? My carbon is going to, if I draw this out, if I drew it out, it would look something like this, right? Okay. It's going to come together here. My carbon's going to have 4 sp orbitals, and I'm going to show you how I know that when I get going here. Okay. So I'm going to draw my carbon here. It's going to have an sp orbital coming out here. It's going to have an sp orbital coming out here. It's going to have an sp orbital coming out here, and it's going to have one coming out here. Okay? When I connect that with my chlorine, chlorine will also have an sp orbital, and they're going to overlap here, end to end. Okay? And then it's got these other ones out here that are going to have the lone pairs of electrons in them. So this is going to be a lone pair, lone pair, lone pair. And then we just repeat that. Lone pair, lone pair, lone pair. Not a great drawing on that last one, sorry. Lone pair. I'm going to have overlap here. Lone pair, lone pair, lone pair. And then an overlap here. The lone pair, and lone pair. Okay, so this is my carbon tetrachloride. These overlap here, where they overlap, that is called a sigma bond. So where they overlap, end to end, is called a sigma bond. We represent that with a circle with a little line coming off of it. So it looks like a guy with a little hat, almost. That's sigma. I think it's a lowercase sigma in Greek letters, yeah. But that's the lowercase. The uppercase looks like a uppercase kind of messed up E, like that, something like that. That's the uppercase. That means something different, okay?
That gives me
Sigma is just that's for you.
All right, so that's where they overlap end to end. Anytime we have sigma bonds, they're going to be this sp hybridization. Okay. We also have something called a pi bond. And the pi bond overlaps side to side. Okay. So now I'm going to do, maybe, I'm going to do CO2 for you. Okay. If I draw the Lewis dot diagrams for CO2, it looks something like this. Okay. My carbon is in the middle. When we have these double bonds here, okay, we can't have sigma bonds there and we can't hybridize. These have to be called, we have to have what's called a pi bond here. Just like in math, it's the same idea. Pi bond. This must have a p orbital. Hot flash. So if I'm drawing my carbon here, I can only have 2 hybridized orbitals coming off because I have to keep 1 for this pi bond and 1 for this pi bond. Everybody cool with that?
You have 2 pi bonds in that.
Yep, there's 1 over here and there's 1 over here.
And then, like, hypothetically, if there's a triple bond, then it's just
There would be 2 pi bonds and only 1 of these would hybridize. Okay, I can do one of those in a minute too if you want. Yeah, there's going to be sigma bonds. This is a sigma bond here. This is a sigma bond. Your first bond is always going to be a sigma bond. Anything after that is going to be a pi bond. So this is a sigma. This is a sigma. Pi, pi. Pi requires a p orbital. P, pi, pi, p. I'm drawing it right now, buddy. Okay. So I've got my 2 hybridized orbitals here. And if we're looking at the electron configuration for carbon, okay, it's going to look something like this, right? Okay. But remember, a couple of these are going to hybridize. I've got to leave this one open and this one open for this bond and this bond. So I have to keep these as p orbitals here and here. All right, so watch. So when I have this, these are hybridized. I'm also going to have 2 over here that I'm going to have a pi bond here, and I'm going to have a pi bond over here for this guy. Okay, these are my p orbitals that have not hybridized. I haven't got them bonded yet. I haven't brought oxygen on board yet. This is a p orbital, p orbital. These are sp orbitals. Everybody cool with that? Okay. So now what I'm going to do is I'm going to start drawing my oxygen and bringing him in. He only has 1 pi bond. He has a sigma bond and then 2 lone pairs. So my oxygen, I'm going to have 3 of these hybridize. And I'm going to leave 1 as a p bond for that pi bond right there, or a p orbital for that pi bond right there. Okay. So I'm going to bring this oxygen in here. I need to rotate him around. He's going to connect right here. I'm going to have this one. Oh, that didn't separate. Shoot, that's not good. I'm going to have one of these go right here, and that's going to have a lone pair of electrons. So I'm just going to do a LP here so you kind of know what's going on with that guy. And this is going to be a lone P. And that's these guys right here. I just couldn't get them to swing around for me the way I wanted them to. Okay. Then I'm going to essentially duplicate that whole thing. Control C, Control V. I'm going to swing it around. Oh, no, that didn't work out so well. Best laid plans, you guys. Okay. So here are my 2 oxygens in place right now, with the exception of the pi bonds. Okay. So right now I have a sigma bond here and I have a sigma bond here. Cool. That's this bond right here and this bond right here. Now what I'm going to do is I'm going to bring in my P, I'll try to anyway. No, this let me. There we go. Control C, Control V. Now I'm going to bring these guys in. Okay. Sigma bonds bond end to end. Pi bonds overlap side to side. Okay. So now this carbon is going to have one here with this oxygen, and they're going to bond side to side. And the carbon is going to have another one over here, and it's going to bond side to side with this oxygen. And these are pi bonds then. And we need p orbitals to do that. So right here is a pi bond, and here is a pi bond. That's these.
It bonds where? Like, where would you place it? Because you have one, like...
You're not going to have to ever draw these. This is just explaining to you the idea. Okay? So you're never going to have to draw these things. Okay? I'm just trying to explain to you what's happening. Okay? So don't get too worked up about how. You're not going to have to draw anything like this. I'm just trying to explain to you that they bond end to end. Sigma bond this way. Okay? So let's look at different types here. Okay? And let me take you through how to figure this out. All right? So here, and they'll ask you, what is the hybridization of a specific element? Okay? So if we want to figure out the hybridization of this oxygen, what I tell you to do is I tell you to hold up 3 fingers. Okay? Do you remember this from honors? Okay? Anywhere that you see a pi bond or a double bond on that atom, so if we're talking about oxygen, take down a finger. So for this oxygen, it's going to be up. Oh, we don't want to do that. Let's get this. The oxygen, we have 2 fingers up. It's going to be sp2 hybridization. Okay? Huh?
What page are we on?
The bottom of page 2.
Oh.
For our carbon here, we hold up 3 fingers. We take 1 away for this pi bond, 1 away for this pi bond. So its hybridization is sp.
I understand this, but like, why do we know?
Because you have, when you're trying to figure out the hybridization, it can be either sp, sp2, or sp3. So I'm trying to teach you how to figure out what to put up there for the exponent.
How come it can't be like sp4?
Because you can't hybridize 4 p orbitals, you only have 3 to hybridize.
So any bond has a hybrid orbital?
If it's a hybrid orbital, it has to have an sp orbital in it. Sp is the hybrid orbital. That's your single bonds or your lone pairs.
What if you found like a orbital?
What?
What if like when you're writing out like if you're doing magnesium or it like ends in an S orbital?
You don't, because this is only with covalent bonds, and covalent bonds are going to have, yeah.
So all molecules have hybrid orbitals because they have bonds, right?
Oh, what, honey?
Molecules?
Yes, molecules, yep. Because those are your covalently bonded materials.
So this doesn't apply to metals? Just
No, it's just covalent bonding. And remember, covalent bonding is nonmetals. Okay?
That makes sense.
All right. So if we're looking, hydrogen doesn't hybridize because it only has an s orbital. Okay. Carbon, though, this carbon, if I hold up 3, for my P's, I have to take one away for this double bond. So this carbon is going to be sp2. What is my oxygen? sp2. Okay. So carbon here, what is it? sp. This one is sp. This one is and sp3. Okay. Now they will also oftentimes ask you how many, like in this structure, they will ask you how many sigma and how many pi bonds are present. So how many sigma bonds and how many pi bonds are present in this structure? And then how many sigma? 9. Okay, see how you figure that? Anywhere that it's a double or triple, whatever that is beyond the single, it has to be a pi bond. Good?
Wait, so SP?
SP is the hybridization. That's if the, remember for this one, we would need to have one SP orbital here for the sigma bond, and you would have that hybridized going over to the hydrogen. So the hydrogen would have an S coming off of the carbon. You would have an SP orbital over here. You would also have an SP orbital coming over to this other carbon, and then you would have 2 P orbitals that didn't hybridize because you need them for the double and this, or the double and the triple bond. So hybridization and bond type are different. Okay, hybridization is the orbital, and this is what type of bond it is. Ellie.
How did you count the sigma bonds?
Anything that's not a double or triple bond is a sigma bond.
Okay.
So 1, 2, 3, 4, 5, 6, 7, 8, 9.
Okay.
And then my 2 pi bonds are the double and the triple here.
Okay.
Okay. So over here, count these sigma and pi, and then figure out what these carbons are as far as they're concerned. And then we'll talk about bond length. That one's easy. Bond order. I gotta put my glasses on because I can't tell a double from a triple without them on. Okay, here we go. Did you get the same thing? Yep, making sense? Okay, so let's figure out hybridization here. This carbon is sp2, sp2, sp3, sp3, sp, sp. What about this hydrogen? It doesn't hybridize because it only has an S. Okay? How are we feeling about hybridization? Sigma and pi bonds. Good? All right. Let's talk about, that was my sigma and pi. We talked about how they overlapped. You guys can go through those notes further if you want. It's just easier for me to talk to you about it when I'm drawing it, I think. All right. Bond strength. This is a concept that people have issues with. Okay? A sigma bond, that end-to-end bond, is stronger than this side-to-side bond. Think about if my hands are like this versus like this. It's easy to pull this away. This is much harder. Okay? But if you have a sigma and a pi together, that's going to be stronger than just a sigma. Okay? So a single bond is weaker than a double bond, which is weaker than a triple bond.
Triple bond's the strongest.
Triple bond's the strongest. You can't get a quadruple bond. That's coming next. I know that question's coming next. Sigma bonds are stronger than pi bonds. But a sigma and pi together are stronger than just a sigma. Are Are you good?
The sigma and pi bonds, that's just a double bond, right?
A sigma and a pi together would be a double bond. A sigma and 2 pi would be a triple bond. 2 pi r. All right.
That's the circumference of a circle.
Sigma bonds are free to rotate. So you can have this molecular rotation here, which we're going to get into in another chapter. Double bonds and triple bonds aren't, though, because it's like your arm. You can only rotate it so far, and then those bones won't let you go any further. Okay, they're kind of locked into that spot. Okay, because you got a double bond right here, right? You got 2 bones coming off here. You can't just keep rotating that around and around like your wrist. You can rotate around and around, but this you can't. Okay. All right, bond order. Seems pretty obvious, right? Single bond is 1, double bond is 2, triple bond is 3. And the way I get you to figure out how this works is, if you're trying to figure out the bond order for this molecule here, for the central atom, the bond order here, you've got a double bond and a single bond, right? So I tell you, count up how many bonds you have. How many bonds do you have here? 1, 2, 3. And divide it by your bond sites. That's your bond order. Okay? Because reality is that it's kind of a mashup between these two. That electron's constantly kind of flipping back and forth between these, and it's kind of between that as far as the bond order is concerned. Okay? So here, if we're looking at nitrogen, we've got how many bonds here? 4 divided by 3 bond sites. That's your bond order. Yeah. Okay. So here, do the molecular geometry, figure out the bond order, figure out the angles, figure out everything that I've taught you, because we're done with this chapter now pretty much. Now we're just practicing for the next few days. That's all we're doing for the rest of the week is practice. I'm not teaching you anything new.
Do we have a lab this unit, or is it just practice?
No, there's no lab this unit, but next unit there's like at least 3.
Oh, do we find the bond angles or do we find the bond?
Whatever you want to do. I'll do everything on this sucker. So we get out of here at 25. Yeah, we got plenty of time. So the next few days, like all we're doing is you're just coming back in and we're working through problems. Okay, you're going to work through, you're going to work through, you're going to work through. By Friday, I want everything in that entire packet done. Okay?
Wait, no, we have a test Thursday?
Nope, test is Monday of next week. Okay? So you literally have 4 days, and that includes class time, to work through the rest of this packet. Okay? All we're doing, you were yelling at me about there being so much, but I'm not teaching you anything else. We're done teaching stuff. Okay? You're just practice. You're working at your own pace. And by Friday, I wanted you to try to have everything done so that we can clarify any questions you have.
Sounds like a player saying.
What's wrong, Matthew?
That's so much.
You're working together in class for today,
I
and
missed that part.
there's nothing. I'm not doing anything else in class.
I thought that we were just doing this on our own.
No, there's nothing else that I'm going over in class. You've got class time for the rest of the packet. You can work together in pairs. You can work whatever you need to do. I'm here to ask questions. What I'm going to do is I'm going to open it up for questions at the beginning of the hour tomorrow and Thursday and Friday. And all we're doing is working through the problems that you're stuck on. Okay? And I'm going to upload all my answer keys so you have everything. And then it's just work time for the rest of the day.